Hi guys, it's Miss Burns here, and we're going to go ahead and take a look at our first lesson for MAT202, which is Chapter 7, Section 1, and we're looking at areas in a plane. And I want to just remind you that back at the end of Calc 1, probably the last unit in the course, we looked at getting the area underneath a curve, bounded by the curve and the x-axis. So let me give you an example here. So let's say we have the function y equals x squared, and we wanted to know what the area is between the function and the x-axis, say from 0 to 2. So that would be, you can kind of imagine where I'm outlining here, that little wedge right here. Since it's not a regular geometric figure, we have to use calculus to get it, and that's where this technique comes in. You may remember that what we did is we added up rectangles, technically is what we did. So we thought about subdividing this space into infinitely small rectangles until it filled the entire space from 0 to 2. And how do we add up the sum of all those rectangles? Well, that's the integral. So when you think integral, you want to think summation. So for this example, oops, let me go back. For this example, we would be looking at, I'm trying to get the screen so you can see it here. We would be looking at the integral of the function x squared from 0 to 2. All right, so what if we're looking at two curves that intersect at certain points, and we want to find the area between or bounded by these two curves? So I've got the function y equals 2 minus x squared and y equals negative x. So these are the two functions, a parabola and a line, and they intersect at two places. So what we want to do is find the area bounded by these two curves. So again, we can think of it as splitting it into different sections, or think of it as using rectangles. So think of that vertical strip that I have on the screen as a very thin, tiny rectangle. So the length of this strip, and by length, I think what they really mean is the height. That's probably how I would describe that. So the distance from the top to the bottom. Think about the way I've written this. Do you agree that the height here would be y1 minus y2? So in other words, whatever the y value is here minus whatever the y value is down here, that would give me the height of this rectangle, or the length of this rectangle. And so substituting in the functions, that would be 2 minus x squared minus the other function, negative x. The width of the rectangle would be a very, very small change in x, so we would call that just dx. So the width would be some tiny, tiny change in x that we would just call dx. So the area of that rectangle, or the area of that strip, would be the length times the width. Here it is again, kind of superimposed. So the height or the length is y1 minus y2. The width is dx. So length times width would be 2 minus x squared plus x. Remember where that came from. That was 2 minus x squared minus negative x. Turned into 2 minus x squared plus x times the width, which is dx. Well, how many rectangles fill up this space? There's an infinite number of rectangles, and so that's where the calculus comes in. So we're going to integrate the function from the points of intersection, -1 to +2. So -1 is the x value over here where the functions intersect. +2 is the x value over here where the functions intersect. And then the function, the integral of 2 minus x squared plus x, that's the length, times the width, dx. And so if we integrate that, that'll get us the area bounded within that region. So how do we integrate this? Remember, we use the fundamental theorem of calculus. So the fundamental theorem of calculus says we find the antiderivative for these three functions. So 2x minus 1/3 x cubed plus 1/2 x squared. That's the antiderivative of each of these parts. And then the fundamental theorem says we evaluate it at the upper limit of 2 and then subtract the value at the lower limit of -1. So if we plug in 2 for all these x values, we'll get 4 minus 8/3 plus 2, minus, if we plug in -1 for all these x values, we get -2 plus 1/3 plus 1/2. And I encourage you to pause the video here and actually do this for yourself on your paper. Make sure you agree with all these numbers. And I'll skip the details here, but if we simplify common denominator, we end up getting a value of 27/6, which reduces to 9/2. So that is the area bounded by this parabola and this line from the points of intersection where x is -1 to x is 2. So in general, if we're finding the area between two curves It's going to be the integral of the function from a to b, so a and b would be the points of intersection, of the top function minus the bottom function. That's always going to get us that length of that rectangle with respect to x dx. That gets us the width of each of those little tiny rectangles. So this isn't something you would have to really think about and memorize. It's going to be kind of natural as we work through the problems together in class. You'll get the pattern. It's always the top minus the bottom, and it follows that same pattern every time. All right, so let's take a look at this example. So we've got two functions. This time we've got y equals the square root of x, so that's the radical function here, and then y equals x minus 2, that's the line. I've put this black line here just to sort of subdivide this into two regions, and you'll see why I did that in just a minute. So if we look at it this way, top minus bottom, the reason I put this black line here is because what I wanted you to notice is that from 0 to this point right here, where this x value would be at x equals 2, that would be the x-intercept right there, we're only looking at the radical. So the function itself is just the radical, and then if you want to think of it as the lower function is the x-axis, or 0, y equals 0. But when you get past that point, you've got two functions again that you're working with. The top function is the radical function. The bottom function is the line, y equals x minus 2. So to figure this out, I'm breaking it into two different parts. So the integral from 0 to 2 of just the square root of x dx, that accounts for this first part of the function. Remember, the lower function is 0, so you can think of that as the square root of x minus 0. For the other part, I'm going from x equals 2 to x equals 4. Where I'm getting this 4 from is that would be the x value for the point of intersection. And we can practice this a little bit in class, figuring out how to get these points of intersection out algebraically. But for now, you can just take my word for it. This would be up here. This point would be where x is 4. And so this would be the top function, the square root of x, minus the bottom function, x minus 2. And so we would apply the fundamental theorem, and we would integrate that and get a value there. Well, the reason I wanted to introduce this example is to show you we could do this a little bit differently by looking at it, I guess, kind of sideways. Instead of using a vertical strip, think of using it as a horizontal strip. And if we do it this way, so instead of thinking top minus bottom, if we think right function minus left function, two things here. We'll be integrating with respect to y, because now the horizontal strip is subdividing the y-axis this way, the little widths of each rectangle, because the way it's oriented would be broken up values of y. But also, instead of thinking top minus bottom, we're going to think right function minus left function to get the length of this strip. And so to do that, since I've got to now put the function in terms of y, I have to solve both of these functions for x. In other words, I have to make x a function of y instead of y a function of x. So let's do that. So take the function y equals the square root of x, solve for x by squaring both sides, and I get x equals y squared. The other function, y equals x minus 2. We're going to add 2 to the other side, and we get the function x equals y plus 2. So now this version of the two functions is what I'm going to work with in my integral, because I need my integral to be in terms of y, since I'm doing a horizontal strip. So let's go ahead and set this up. So we're going to have the integral of the function, the right function, y plus 2, minus the left function, y squared. So make sure you see that, the right function minus the left function, dy. And because it's in terms of y, my limits of integration have to be in terms of y as well. So the lower value where I'm starting out integrating would be where y is 0, up to the point of intersection up here, the y value would be 2. So my limits of integration go from 0 to 2. The advantage to doing this is that instead of having to set up two integrals like I did before, back up here, I had to set up two different integrals. I can get away with just setting up one integral. I'd recommend using this method if the functions can easily be solved for x. First of all, if they're very complicated functions and it's not easy to get x by itself, it doesn't make sense to do this, and you may have to just do them as separate integrals. But if they're not hard to get the x by itself, this may be a faster method. So let's go ahead and look. So they're pointing out this is your area of each individual rectangle, the length of the strip times the width of the strip. So if we use the fundamental theorem, and the rules are the same, we're just using y instead of x as our variable, but the process for evaluating the integral is the exact same. We have 1/2 y squared plus 2y minus 1/3 y cubed, that's the antiderivative from 0 to 2. And so if we evaluate these all at 2 and then minus the lower limit of 0, when we plug in 0 for y here, we just get 0. I get a value of 10/3. And so the area bounded between these two curves would be 10/3. So general strategy, always make a picture. So that's the first thing. Don't try to do any of these problems without a picture. It would be really difficult to do that and it would take you a lot longer. So just draw a picture and look at what you're dealing with. Decide if it makes sense to do vertical or horizontal rectangles. Again, pick whichever is easier based on the functions and the way the graph looks, and then determine from there if you're using dx or dy. Write the expression for the area of that rectangle. If the width is dx, then the function has to be in terms of x. If the width is dy, then the function has to be in terms of y. And then find the limits of integration by looking at where the functions intersect, the points of intersection. And then, of course, integrate using the fundamental theorem to get your area.